Hi friends, today we are discussing about the electromagnetism. Electromagnetism is a very important topic in 10th class board exam. So most of the students are going to feel fear about the board exams, especially electromagnetism topic. So you will get good marks if you follow and if you read the electromagnetism thoroughly. 100% is very easy, not only in 10th class, in higher classes also it is very important. So shall we start? Right. In our electromagnetism, we need to discuss about that. First of all, old days, all people they thought that electricity is one of the branch of science and magnetism also one of the science. So they are not related with the electricity and magnetism. So both are different type of subjects in their point of view. So but first, given that Oersted. So Oersted is one of the scientists. He given about the Oersted experiment. So Oersted is one of the scientists. He given about the idea of the electricity and magnetism. So all people before Oersted experiment, they thought that electricity is a different subject and magnetism is a different subject. Then Oersted, what he did that he did experiments about that electricity and as well as magnetism, including these two. If he got some idea about this, for this Oersted experiment is there. So he taken as a two Y-shaped wooden sticks. He took this two Y-shaped wooden sticks on a table and he arranged one copper wire on the Y-shaped wooden sticks and he arranged the battery of this positive and negative terminals of the battery to the particular copper wire. Then this copper wire is getting electricity. The copper wire is passing electricity through it. So now, if before that you just observe that he given as a key. The key was opened, means no electricity is enter inside of the copper wire. Then no electricity is present. Then here what he arranged that he arranged the below of a copper wire one compass. The compass is a one kind of the magnetic north and south poles of a magnets of a needle present inside of the compass. So it will show the directions or any magnetic substances are there. So it will attract or repel, each and everything will depend on the. So it will ready to show this kind of magnetic flux and magnetic deflections will present. Then now, so initially no current is passing through the copper wire. That's why no deflections in a compass. Then when we switch on, it is nothing but the key was closed, then automatically the copper wire is getting electricity through the copper wire. The electricity is trying to pass through it, then automatically. So what he observed that this is a compass is showing as some deflections. The some deflections are showing is nothing but something is around it. So when we switch on the key, means when we give a electricity to a copper wire, then surrounding of the electric current, something is ready to appear. It's nothing but is a magnetic material. So magnetic field has to generate. So then that's why he given the idea about the yes, if any current carrying conductor contains some magnetic field around it. So according to this idea only, all the scientists they started doing experiments on the electromagnetism. Now this kind of example we started. This kind of things we started. Then after completion of this Oersted experiment, now we'll go for the magnetic field. What does it mean by field? If any object is there, for example, one object is there. So one is A is the object. It has some influence in a one area. The object is some influence some area that is called as a field. So magnetic field is nothing but without any physical contact or either attraction or repulsion between the two objects. Then it is called as that is a magnetic field. Okay, so this is the area you will write to just around of this object A, for example, around of this A. So some area will be there, it is either attraction or repulsion. This is called as a field of the particular A. So that's why it is a magnetic field, right? So after completion of this magnetic field, now we go for that how to identify the magnetic field and where the magnetic field lines are there. So magnetic field lines are imaginary lines. It will appear. So it is imaginary lines. We cannot identify physical contact, but we can easy to identify with one experiment. What kind of experiment? Just you can say that if you bring any bar magnet, north south poles of a bar magnet, you can bring it. So bring north and south poles of a magnet. Then not only north and south pole, the bar magnet you can bring it. Then you just better to rub in a husk or any dust particles, then it will attract by the small particles. There is a black particles are attracted. So around the particular bar magnet. We already know that small kids they are playing that with a bar magnet. So it will attract the small particles. Then you better to remove all particles of the bar magnet and just pour on a white paper. Then next, bring a bar magnet and keep below of the paper. For example, this is the paper. On paper, you just pour some all particles in it. The next, so the bottom of the paper, the down of the paper, you better to arrange again bar magnet and you better to move here and there. The particles are moving in a straight line. Yes, we call that design. The straight lines are ready to appear as a field lines. So individual line is called as a magnetic field lines. This is the imaginary lines we cannot see directly. With experiment only can explain that yes, how much of field line, how many field lines are ready to present around it. So okay, right. So we got the directions, we got the north and south poles of a bar magnet containing magnetic field lines. But what is the direction of the field lines? So either north to south pole or south to north pole. Now for this one more activity is there. We can easily do that activity. Then once you see this activity, if you need to see, observe this. For example, again we just taking bar magnet on a white paper. For example, this is a board is a white paper. On a white paper, I kept one north and south poles of a bar magnet. Then I want to identify the directions of the magnetic field lines. Then bring one compass. For example, I want to bring one compass. Then compass will shows the deflections if there either attraction or repulsion between the poles. We already know that north pole and south pole both are so like poles. North pole or south pole. They are like poles. That's why it will repel. But north pole, south pole and south pole, north pole is ready to attract. Both are unlike poles. That's why according to this law of magnetism, now we can bring one compass. You can bring one compass, then keep near to the bar magnets. We don't know where we are keeping, but so some area on a white paper near to the bar magnet, just keep a compass. Then it shows some deflections. The way it will try to show the deflection, you can keep a dot on a white paper. Right. So remove the compass and again keep some other area. Yes, you can keep one more dot. It shows another deflection. Then if I am going to bring one more area, yes, it shows one more deflection. Yes, we keep so all dots, so different type of areas will get the different type of dots will get it. If you just remove the compass and once you observe this, so it shows that this is called this is right to show that the direction of a magnetic field lines. It shows from the north pole to south pole. If I am going to just observe that, so magnetic field lines are ready to appear north pole to south pole. So this is the activity we can easy to identify. Yes, how to identify the directions of a magnetic fields in our bar magnet. So after completion of this one, now we go for the we identify the north and south poles of a magnet. What is the meaning of flux? The flux is also there. The flux is nothing but number of field lines are ready to present. For example, one bar magnet is containing some little bit magnetic field or less energetic either attraction or repulsion of the other magnetic substances. Okay, then we feel that the number of field lines are ready to present. is said to be the flux. That is an imaginary line. The flux is also imaginary thing. So that is a, for example, we show this the flux is a pi. The pi is a symbol which shows the flux. Okay, right now. So the flux will present from north pole to south pole the number of field lines. For example, here the field lines are 3. Yes, this is a combination of a field lines. B side it is a flux. The intensity also there, the density is also there. The flux density, it will depend on a flux. So what does it mean? In particular area, how much of flux will ready to present, means how many field lines ready to present in particular area, we said to it is the flux density. The formula will be there. There is a flux density formula. That is simple. It is a flux density. Okay, see here, this is a magnetic field lines from one area. For example, in a particular cross-sectional area, if I consider a cross-sectional area, in a particular cross-sectional area, number of field lines are ready to present. Yes, this is a particular area. We call it as a area is a capital A. That is a intensity formula. The B is equals to the flux density. B is equals to, that is a flux divided by area. How many magnetic field lines are there? It's a flux divided by area. So if I know this problem, if I know this pi is equals to means BA, so B into A. The A will go this side and pi is equals to B into A. So after getting this one, so this is a horizontal direction. Every time if you need to consider as a angle values, for example, angle values are called as a theta. Angle is a theta. If I need to consider as a angle values, the cos or sine values we can take, means horizontal direction lines we can take as a cos. So every time, not only in this equation, the horizontal direction path we can consider that it is a cos theta. The pi is equals to BA cos theta is a flux formula. Then after completion of this one, we will go for the current directions also there. The current is nothing but, for example, if you need to observe that current is in conductors. So is the straight conductors are there and curved conductors also there. The straight conductors are containing electric current. For this one activity is there. For example, if you want to take a one iron stand. On an iron stand, for example, roughly I am going to draw this one. Okay, so we arrange that in the same. On iron stand, we arrange one copper wire. It is a straight wire actually. So here, once you see here on an iron stand, I arranged a straight wire. Then this wire is containing or connecting to a battery, two ends. This is a positive and negative terminals of a battery, and this wire is just passing through a slit of the wooden plate. So this is a current is passing. When we switch on the battery, this conductor or this copper wire is going to contain electric current. Then the nearby the copper wire, if I am going to arrange one bar magnet, is a north south poles of a bar magnet or otherwise compass. So the compass is trying to identify the deflections. What kind of deflections are there? So if I need to just observe the directions of a current, the directions of the currents will be there, and say out of the page and inside of the page currents are there. Out of the page, inside of the current, inside page current, we can easily to identify with a bottle cap example. Just let's discuss about the bottle cap example. What kind of directions of electric currents is there? Okay, there is a current directions I am going to show with a bottle cap example. We can easily to say that, for example, if you need to just open the cap of the bottle, for example, see the directions of the current. I want to see the directions of the current of the page. If I remove just cap of the bottle, see this is a directions. Then I am going to draw this diagram again on board. once you see this is a circular path, just I am going to show that this is the directions what I open the cap. So this is a thing, this is a out of the page current, there is a out. The current is out of the page. If I am going to open the bottle cap, then there is a out of the page current. If the inside of the page current is there, then closing of a cap. Just I will show this again. So when I open the bottle cap, again I am going to just keep it like this, and then once you see this, the direction will change. I am going to show the directions. So this kind of directions is called as a, this direction is called as a inside the page of the current. The current direction of is in inside. Just once you see here. So this is a inside the current. Current is in page input. So page inside is outside the currents are there. Then you can show the thumb rule also there. The thumb rule will explain that what is the directions of the current and surrounding of the current, any magnetic field will ready to generate or not. We can easily say that this I need to show this. My thumb is a directions of electric current. For example, you see here all, see this is a thing we can observe that this is a thing. The thumb will indicate as a direction of a electric current or any conductor. Then surrounding of the conductor, once you see, so this is the surrounding of the conductor, then curved fingers will explain or showing as a, so these are the electromagnetic substances, means there is a surrounding of the conductor, magnetic field has to generate. So then I am going to show like this. So this is a, these fingers are ready to appear and showing as a magnetic field around the conductor. This is called as a thumb rule. So thumb direction is a electric current direction, and the curved fingers are ready to show that it is a magnetic field around the conductor. Then if for example the number of field lines are ready to present, I will show the one more activity. So here this is a only single wire, the single straight wire is ready to containing magnetic field around the conductor. Then the number of field lines are there. For example, curved conductor is there. Then I will show that conductor is a curved one. The curved one is ready to get more magnetic field. For example, if you arrange any wire is a curved wire. Simple logic. This area will having some magnetic field, and as well as some more other area is also, these are all different areas also ready to containing magnetic field around the conductors. Then the combination of all magnetic fields are ready to generate the more magnetic field around it. It means less area, it will generate more magnetic field. How to explain, how to identify this magnetic field with experiment or with our fingers? Easy to explain that. For example, once you see again, so my thumb is right to indicating as the same as it is a electric current, it's a direction of electric current. But this now these curved fingers are there. These curved fingers are right to explain that number of turns of a, for a means let's say what is the first finger will indicate as a one turn, and second finger is as the second turn, third turn, and fourth turn. Means the four number of turns are there. Then these are all number of turns of a wire. It will indicate that magnetic field direction. So here this is a magnetic field. The magnetic field direction is a, this is a thumb will indicating as a magnetic field, and now it should be the number of fingers will explain that the curved fingers are going to show that it is a magnetic field around of the conductor. Then we can say that that is called as this kind of arrangement we call is a solenoid. The solenoid is nothing but it is a spring type of arrangement. Once you see, this is the arrangement of a solenoid. Okay. This is a solenoid. This is a solenoid. Solenoid is nothing but it is a spring type of element. All people we already know that is the springs. The spring is a look like this. For example, in our pen also, if you just press and pens are there, in the pen also it will be ready to appear. This is a spring there. This kind of spring. So number of turns are there. For example, in this spring, the number of turns is n. So n turns are there. Then what is mean by flux? So here it is also look like a north and south pole of a magnet. And it is also ready to contain that it is a north to south pole of a magnet. There is a magnetic flux will be there and magnetic field lines also there. Okay, so in our competitive exam they may ask that the north to south pole of a magnets are magnetic direction, magnetic field directions are there. But what about the solenoid inside the part? Any directions can change. Yes, it should be changed say in a solenoid. Inside the solenoid, the direction of the magnetic field lines should be south pole to north pole. Outside the part only it shows as a north pole to south pole. In every area, the north to south pole, the flux or magnetic field lines will be present. But except the solenoid inside the area means hollow shape. Then inside the area is the south pole to north pole, the direction of the magnetic field lines will present. So that is one of the specialty of the magnetic field lines in a solenoid. Then okay, write out in a for example, in this magnetic field, if I am going to arrange one magnetic field is there. So this is a magnetic field. This into symbols always says that it is a magnetic field. If any charge want to just ready to enter into a magnetic field in a horizontal direction, the charge will show as a small q and the speed of the charge is a v or velocity. Then magnetic field intensity or density will shows as a capital B. From this we can easily to identify the formula. F is equals to QBB. QBB. Force is equals to means on charge some force is acting according to the magnetic field density. So the field density is ready to appear some force on a charge. That's why. So F is equals to QBB. We already know that the Q is a charge and V is the speed and B is a magnetic field density. Then F is equals to QBB. In a horizontal direction is there, but one thing, the force can appear in a vertical direction, so the force will appear on it. So that's why if I consider the angle values, then F is equals to QBB sin theta. QBB sin theta. So F is equals to QBB sin theta will be there. Then this is a final, and if the theta value will be 0, theta is a 0 degrees, then automatically what will happen? The force will be 0. Because sin 0, 0, then 0 will multiply with a QBB, then whole and so the F value became 0. For example, the theta value is a 90 degrees. Then what is that? F is equals to QBB. Is a maximum current or maximum force is acting on it. So after completion of this one, now we will go for the right hand rule. The right hand rule is also ready to explain that. Right hand rule. So the right hand rule will explain the electric field and as well as the magnetic field. So both are ready to appear in a particular area. What is the resultant force direction? The force will be the electrical forces and as well as magnetic forces will present. What is the resultant force? We can easily to identify with this kind of right hand rule. Okay. Now the right hand rule will shows like this. This is a finger. I am going to show that. So this is a first. Once you observe that this finger will indicating as a electric current passing to the conductor. This is a direction with the pointing finger is a electric current direction, and then the middle finger is right to show that it is a magnetic field density, is a B value. Is a middle finger will shows that it is a B value, and I value or charge velocity or speed will shows with a pointing finger. Both are perpendicular to each other. Yes or no? These are the both are perpendicular to each other. Then next, if these two are perpendicular to each other, ready to apply in one area, what about the resultant force? Means the resultant force will shows as a, so this kind of the thumb finger direction is a resultant force between the, this is a magnetic field density and electric field, means current. So these resultant force are ready to appear perpendicular with both, means if you consider any direction, both are ready to present in a 90 degrees, means there is a perpendicular to each. So this is a right hand rule. We can easily to identify the how much of force is acting on it. So then, for example, if you just observe that F is equals to QBB is there. If I need to consider one area in a one conductor is there, this area I just arrange one straight line of a conductor, means this is a conductor will shows it is a straight wire, it is a copper wire in this field, right? If when we arrange this straight wire containing no electric current in it, that's why it is a straight wire. Then when we apply the, so the same thing, so I'm going to show this one. For example, same thing, when we switch on the battery, means there is a conductor containing electric current, then so resultant area, so it should be ready to appear as a some different type of direction, means it will ready to move in a one area. So what is the forces acting on it? If we have any forces are there, means yes. So we know that if F is equals to QVB sin theta, you all people you know this, just now we discussed, and this is the length of the conductor is a small l. Then what we know, this V is equals to, the velocity is equals to displacement by time, or otherwise V is equals to, so what is the displacement here, or the length is a displacement, L by T is a time is a T. So then Zane, now instead of V I am going to substitute the L by T. The F is equals to Q into L by T, then into B sin theta. Then next step I want to write the F is equals to Q divided by, can I write this is a T into L B sin theta. Then in this Q by T is nothing but what is that? We already know that I is equals to Q by T, charge by time. Then F is equals to, so instead of Q by T I am going to write I, means I L B sin theta, or otherwise F is equals to Bill sin theta. This is a formula to find out the resultant force acting on a wire or conductor, straight conductor. So this is the thing we can easily to observe the, so how much of force is acting on it. So in our exams they may ask the questions about the force. F is equals to BIL sin theta. So F is equals to QVB sin theta. In electromagnetism, most probably F is equals to Bill sin theta and F is equals to QVB sin theta. These two formulas are useful in every areas. So we can change according to that